Welcome to WikiPodcast. Okay, let's unpack this. We're taking a deep dive today into something, well, really fundamental, looking at a stack of sources covering some incredibly complex ideas in Physics Thinks articles, research notes, even some of your own thoughts on the subject.
Right, our mission, to sort of cut through the complexity and pull out the really important nuggets about the edges of our understanding.
Ah,
The known unknowns in the universe, you could say?
exactly. It's about getting a shortcut to being well informed on some of the biggest questions out there, maybe find a few surprising facts, and hopefully get enough clarity to make it all stick.
And today, yeah, we're exploring the limits of physics, because despite all our progress, there are these profound mysteries that current theories just can't fully explain. And these aren't small details. They're like fundamental gaps in our understanding of reality itself.
So, what stands out to you when you look at the sheer number of unsolved problems? It feels like we know so much, but then you see this lift of things we don't know, and it's still huge.
Well, what's fascinating here is that these problems fall into different categories.
Hmm.
Some are theoretical, meaning our existing theories, our best models, just can't explain an observation.
Okay.
Others are more experimental, where we struggle to actually build experiments sensitive enough to test the ideas that people are proposing.
Right, like our theories point to something, but we can't actually see it, or maybe we see something that the theory totally didn't predict.
Precisely. And the source material highlights these broad areas where the unknowns live. We've got these really fundamental questions in general physics, like the search for a single theory of everything.
A theory of everything. Like one equation to rule them all. Is that the idea?
Something like
Yeah.
that, yeah. A framework uniting, well, all physical aspects of the universe. Then there's the whole realm of quantum gravity, which is all about trying to merge quantum mechanics and general relativity.
Oh, okay. That's where things get really weird, isn't it? Like, is space-time fundamentally smooth, or is it kind of chunky, pixelated at the very smallest scales?
That hits on a key question. How do we reconcile these two, incredibly successful but ultimately different pictures of reality, quantum mechanics and general relativity? This plays out in challenges like understanding black holes. Do they really emit thermal radiation, like Hawking predicted? And what happens to information that falls into them?
Right, the black hole information paradox, that's a huge one. Quantum mechanics says information can't just vanish.
But relativity suggests it could behind the event horizon. It's a major puzzle.
And singularities. What about naked singularities and this cosmic censorship hypothesis? Can those even exist? Or are they always hidden?
Good question. And then there's backwards time travel, the chronology protection conjecture. Does physics itself actually forbid it, build in some kind of protection?
So many fundamental questions there. What about looking outwards cosmologically?
Ah, yes. Cosmology and general relativity hold some of the biggest unknowns. The most famous are definitely dark matter and dark energy. We infer they exist purely from their gravitational effects. Dark matter seems to hold galaxies together, affecting their rotation.
Uh-huh.
And dark energy is causing the expansion of the universe to speed up.
But we don't actually know what they are. Are they particles we haven't found yet? Or maybe gravity works differently on large scales?
Exactly. And why is their density, their influence, so similar right now, relatively speaking, given that they evolved differently over cosmic time? Feels like a bit of a cosmic coincidence.
Yeah, that is strange.
It does seem peculiar. Other cosmological puzzles include, well, the ultimate origin and future of the universe itself. Its true size and shape. Is it finite or infinite? Then there's the matter-antimatter asymmetry. Why is there so much more matter than antimatter left over from the Big Bang? They should have annihilated each other.
Right, we shouldn't really be here if they were perfectly balanced.
Precisely. And the horizon problem. Why does the distant universe look so incredibly uniform in temperature, even in regions that shouldn't have had time to interact or exchange heat?
Yeah, the universe shouldn't look so smooth based on the standard Big Bang model alone. Inflation is offered as a solution, right?
Inflation is the leading idea, yes.
Hmm.
It proposes an incredibly rapid expansion early on that would smooth things out. But the sources do acknowledge. People explore other possibilities too.
Okay, moving from the vast cosmos down to the very small. What about high energy and particle physics?
Also full of fundamental questions.
Yeah.
The hierarchy problem is a classic. It basically asks, why is gravity so incredibly, ridiculously weak compared to the other forces, like electromagnetism?
Like you always hear, you can pick up a paperclip with a tiny magnet, easily overcoming the gravitational pull of the entire Earth. why that huge difference in strength? It seems unbalanced.
Exactly. It's a massive discrepancy that many physicists think points towards new physics, maybe extra dimensions or supersymmetry.
Huh.
Other particle mysteries include things like the exact mass of neutrinos. We know they have some mass now, which was a surprise, but getting the precise value is tough.
Yeah.
And do protons decay? Even incredibly slowly, over vast timescales. Some theories predict they should. We haven't seen it yet.
So maybe our protons aren't forever.
Maybe not. And understanding things like quark-gluon plasma, the state of matter just after the Big Bang, and color confinement, why we never see quarks on their own. And, you mentioned this earlier, why are there 3 generations of quarks and leptons, these fundamental families of particles? Why 3? Not 2, not 4.
Wait, 3 generations? Like different sets of fundamental particles? That seems arbitrary. Why just 3?
It's a completely open question. Is there a deeper reason? Or is it just how it is? We don't know.
Wow. Okay, what about condensed matter? Things we can actually, hold.
Well, a huge goal there is high-temperature superconductivity, finding materials that can conduct electricity with absolutely zero resistance, but at temperatures much closer to room temperature than the incredibly cold ones we need now.
Room temperature superconductors. Yeah, that would completely change everything. Energy transmission, computing.
It would be revolutionary. And even something seemingly more mundane like fluid dynamics still holds deep mathematical problems, like proving rigorously that smooth, well-behaved solutions exist for the Navier-Stokes equations that describe turbulent flow.
So even understanding how water swirls down a drain or smoke curls up is, at its heart, a really deep physics and math problem.
It is, surprisingly deep. It's actually one of the Millennium Prize problems in mathematics.
Huh. And what about the real foundational stuff? The interpretation of it all.
Ah, yes, the foundations of physics. This gets almost philosophical. How do we actually interpret quantum mechanics? There's the measurement problem. What counts as a measurement that forces a quantum system to collapse from possibilities into a definite state?
Right, the whole observer effect thing. Does consciousness play a role, or is it just any interaction?
Big questions. And of course, the error of time. Why does time seem to flow only in one direction, always forward, always tied to increasing entropy or disorder? Is there a fundamental reason for this directionality, or is it just a feature of our universe's initial conditions?
It feels so fundamental, yet explaining why is hard.
It really is. But, it's important to remember, looking through these sources, that progress is constantly being made. This isn't just a list of things we'll never know.
Oh, that's encouraging. Like what mysteries have been, maybe not solved, but seen major progress recently, say in the last 30 years or so?
Absolutely. The sources point to some major experimental wins. Gravitational waves, predicted by Einstein a century ago, were finally directly detected by LIGO and Virgo. That was huge.
A whole new way to observe the universe opening up.
Exactly. Bose-Einstein condensates, this weird quantum state of matter, were created in labs. Pentaquarks, exotic particles made of 5 quarks, not the usual 2 or 3, were definitively discovered.
5 quarks, okay.
The Higgs boson was found at the LHC, confirming the mechanism that gives fundamental particles mass, resolving the electroweak symmetry-breaking puzzle.
Right, the God-particle controversy aside, it was a massive confirmation of the standard model.
It really was. And quark-gluon plasma, that primordial soup from the early universe, has been created and studied in heavy ion colliders.
So these are massive achievements, moving things from just theory or prediction into actual observed reality.
Definitely. And we've also resolved several nagging anomalies that had scientists scratching their heads. The solar neutrino problem, for instance. We were detecting fewer neutrinos from the sun than our models predicted.
Where were they going?
Turns out they weren't missing. We discovered neutrino oscillation, the fact that neutrinos can change flavor or type as they travel. So the electron neutrinos from the sun were turning into other types on their way here.
So the neutrinos weren't missing, they just, changed identity mid-flight. That's amazing.
It is a Nobel Prize-winning discovery. Then there was the Pioneer anomaly, this tiny, unexplained extra acceleration seen in the Pioneer 10 and 11 spacecraft as they left the solar system.
Oh, yeah, I remember that. Looked like new physics for a while.
It did. But it was eventually pinned down to something more mundane, anisotropic thermal radiation. Basically, heat radiating unevenly off the spacecraft itself, giving it a tiny push.
Ah, so it was the ship itself, not new forces.
Seems so. And remember the faster-than-light neutrino claim a few years back from opera?
Vaguely, yeah. Big news, then retracted.
Right. That was eventually traced to a faulty fiber optic cable connection and a clock issue. Experimental error.
Okay, so sometimes it is just checking the equipment.
It happens. And the Hipparcos anomaly, a small discrepancy in stellar distance measurements from a satellite, was resolved by more sophisticated data analysis, accounting for subtle effects.
So it's a mix then. Some unknowns turn out to be genuinely new physics, like neutrino mass, while others are about refining our measurements or understanding our instruments better. It shows the scientific process in action.
Precisely. And this whole exploration into the limits of physics, pulling from these sources, really reminds us that science isn't static. It's a dynamic, ongoing process. These unsolved problems aren't failures, they're the frontiers. They're what drives new research, inspires new technologies.
Pushes the boundaries of what we can even imagine asking.
Exactly. And pushing human ingenuity.
And I think understanding these questions, even if you're not a physicist, just gives you a deeper appreciation for the universe and our place in it. It really highlights how much more there is potentially out there to discover.
It absolutely does. It helps us appreciate that our current understanding, as powerful as it is still incomplete. It encourages curiosity, critical thinking about the fundamental nature of reality.
It's like looking at an old map and seeing those vast areas marked, "Here be dragons." Except here, it's "Here be fundamental physics." The unknown is actually really exciting.
It is. It's where the next breakthroughs lie. So considering all these profound mysteries we've touched on, from the tiniest particles way out to the largest structures of the universe, here's a thought. Is it possible that some of these known unknowns are fundamentally linked in ways we just haven't conceived of yet? Maybe the solution to one problem, say dark energy, is actually hidden within the answer to another, like the interpretation of quantum mechanics or the true nature of space-time at the Planck scale. Are we looking at truly disconnected puzzles or maybe just scattered pieces of a single, much larger picture that's currently just beyond our view?
That's a fascinating thought to end on. Are the answers connected in ways we don't even realize? Thanks for listening. Write us your opinion in the comments on which of these unsolved problems in physics you found most surprising or thought-provoking. Subscribe to the channel to help more listeners reach our deep dives. Thank you, and have an amazing day.